Hey guys, sorry to be sick all week, but I hope you're doing okay. I'm gonna try to walk you through this worksheet real quick. You watched the Professor Dave video, where he kind of talked through two-dimensional motion. And the big idea with two-dimensional motion is that what happens horizontally and what happens vertically don't affect each other. What that means is that nothing that we're going to do in this week and next week is actually new. We've already done horizontal stuff, we've already done vertical stuff. And during the forces unit, we've learned how to split something that's happening at an angle into horizontal and vertical. And so that's all we're doing. We're just taking it back to the big three and applying it there. Um, there's kind of two big types of problems that you're going to see in this class, when it comes to 2D motion, and we're going to work through two of each of them on this worksheet. So the first ones are where something is on a cliff and we're launching it off of the cliff and it comes and falls. Sorry, I left my Apple Pencil at school, so you have actual writing today. And the other kind is where we're on the ground level, we launch it at an angle, and it comes and hits the ground again. Okay, so questions 1 and 2 today on this worksheet look like this. Questions 3 and 4 look like that. All right, let's get started. I'm going to ask you along the way to kind of pause and try the problem for yourself before you listen to the remainder of me doing the problem. I'm also going to today use the Desmos app on all of our quadratics. Obviously, you have other options. And I may pause this a couple of times. So if there's weird splices, I'm sorry. I'm just trying to get this done for you. All right, let's go ahead and take a look. A baseball is launched horizontally off a 20-meter tall cliff at a speed of 20 meters per second. And the first thing I'm going to ask us to do is to think about, what do we know in this problem? And there's horizontal information we know and vertical information we know. And so at the very beginning of this, you can see if we've got the baseball being hit off the top of the cliff horizontally, then its initial velocity is all horizontal. None of it is vertical. It's not pointing up or down. Everything that's happening at that very first moment is horizontal. And our horizontal and vertical accelerations are always the same and always very boring. Nothing's happening to accelerate it horizontally, but it does have gravity accelerating it vertically. These will always, 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 please write this in your notebook, always, always be the accelerations on a two-dimensional motion problem. All right. I don't know anything about final velocity, and there's nothing in this problem about final velocity, but I do know. So I've already covered the 20 meters per second that was over here. I do have this 20 meters tall cliff, which, what does that mean? It means that when I reach the ground, my change in position vertically is going to be negative 20 meters. Why negative? Well, because it is falling. All right. So this is the very first thing that we will want to do when we do one of these problems, is fill out what exactly we know and what we don't know. And then on each subsequent problem, we're going to ask ourselves, is this a horizontal question or a vertical question? And then we're going to use only the horizontal information or only the vertical information to solve it. And the secret to understanding whether it's horizontal or vertical is that it's almost always a vertical question unless the word horizontal is in the question itself. Um, and so if you don't see that word, assume it's a vertical question. Part of that actually is because of the fact that horizontal is pretty boring. It doesn't have any acceleration, which means it doesn't have any forces that are really driving the problem. Vertically, we do have something, which is gravity, driving the problem and determining what's going to happen next. And that's why vertical tends to dictate, and then horizontal follows. And we'll see that here. All right. So what I'd like you to do is see if you can figure out how long until this ball reaches the ground. And again, I'm going to remind you before you start this, that is a purely vertical question, and we're trying to solve for the time. Okay? So give that a shot. Pause the video now. All right. So, how long until it reaches the ground? This is really the same as if I had dropped a ball from that cliff and asked how long it takes to get to the bottom. So I have an initial velocity, an acceleration, a distance traveled, and I'm looking for a time. And if I look at my big three, then the one that I want to use is number 2. So I'm going to say -20 equals VIT plus 1/2 a t squared. So 0 times t is always going to be 0. This ends up as -20 equals -4.9 t squared. Divide both sides by -4.9. And I'll end up with, getting out my calculator, t squared is 4.08. Please don't forget to take the square root of that. And you'll get that the square root is 2.02 seconds. All right. Next up, I'm going to ask you, what are the horizontal and vertical velocities at the ground? And something I'm going to tell you is, now that we know that the time to get to the ground is 2.02 seconds, this is the only variable that gets to live on both sides of that chart, because it's horizontally at the ground and vertically at the ground at that time. All right. So using what you know, go ahead and try to figure out what the horizontal velocity and vertical velocity at the ground are. Pause the video here until you're done with that. Okay. So the horizontal velocity at the ground and vertical velocity at the ground. We have initial velocities for each, we have accelerations for each, and we have times for each. So we're just going to use equation 1, which is usually our most straightforward equation. VF equals VI plus AT for both of these. All right. For horizontal velocity, remember, we're only going to pick numbers from the horizontal side of that chart. So VI is 20. A is 0. T is 2.02. And since that's 0, we end up with just the same horizontal velocity. And this is always going to be the case because there's no forces acting in the horizontal direction. Nothing ever happens to the horizontal velocity. It's very boring. Things really only happen in the vertical direction. Vertically, things get more interesting. So our initial velocity there is 0, but we do have an acceleration. And so we will need to calculate 9.8 times 2.02, and we'll get that the final velocity is negative 19.8 meters per second. Negative because it's down. So this starts horizontally and it ends still horizontally, but also heading downward. E, I'm going to ask you now, use the Pythagorean theorem to tell me what the total velocity would be. In other words, what the hypotenuse would be. Give the video a pause until you have an answer. All right, so what are we going to do? We know our horizontal velocity and we know our vertical velocity. Horizontal velocity is 20. Vertical velocity is 19.8. And we want to find the hypotenuse. So 20 squared plus 19.8 squared, and then we're going to take the square root of that. So square root of 20 squared plus 19.8 squared. And we end up with, this is 28.1 meters per second. Um, Notice, yes, this is actually negative 19.8. When you square a negative, it goes away, so it doesn't actually matter to the math. All right, so that is the entirety of this problem. What I'm going to ask you to do is work through all of problem 2. Pause this video while you do. It's almost exactly the same conceptually. The numbers are just different. And then I am going to go through the entirety of problem 2. So pause now, work through it. Okay, let's get started. I told you to write these 2 numbers in your notebook, and I hope that you did. Because always, 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 what are our accelerations? Horizontal is 0, vertical is negative 9.8. I have to grab the rest of my information from up here, so I know that I am going to be going down 50 off of this cliff. I also know my initial horizontal velocity is 30, and my initial vertical velocity is 0. It's being shot horizontally off the cliff. Okay. So now, how long until it reaches the ground? That's a purely vertical question. And so I'm going to use equation 2. Negative 50 equals 30. Oh, what did I do here? I am in a vertical question, and what did I try to do? I tried to grab a horizontal velocity. I see this all the time. It's not a big deal, but it's really important that we manage to keep those straight. For the record, it'd be a point or so off. It's not a huge deal. It's not negligible. All right, that 0 turns that into nothing. So now I end up with 50 divided by negative 4.9. So I end up with t squared is 10.2, which means that t is the square root of that, 3.2 seconds. Horizontal and vertical velocity at the ground. Well, again, I just found out that the time at the ground is 3.2 seconds. So we're going to put that over here too. And so I'm really just asking what is my final velocity at that time. This is a horizontal problem because it actually has the word horizontal in it. So that's 30 plus a t, still just 30 meters per second. Remember, horizontal velocity doesn't change. Here, our final velocity is 0 plus negative 9.8 times 3.2, which is going to be negative 31.4 meters per second. So when I'm asked to find the total velocity at the ground, I have 30 this way, 31.4 this way, and I just need to find that hypotenuse. So it's the square root of 30 squared plus 31.4 squared is 43.4 meters per second. There you go. All right. Question 3 gets a little different. So question 3 is where, again, we're shooting this thing from the ground. It goes up and it comes back down. Um, things that change here. First of all, we're going to have to do a little bit of separating into horizontal and vertical to begin with. That's not going to be as easy as just identifying which numbers are horizontal and which are vertical. We may actually have to do some SOHCAHTOA to do that. Secondly, we introduce an element of symmetry here. And we also introduce another interesting point. Okay, so on the previous question, I only asked you about what happened at the ground because that was really the only other interesting place to ask about. I could have asked about any of the different heights or times in between, but none of them are particularly interesting. We mostly want to know when things land. And so uh, that's what we did. Here we have two things. We have, yes, when it lands again on the ground. That is a very interesting time. We also have what I'm going to call the peak. So when it's at its very highest. And the thing to know about the peak is that this is when the vertical velocity is equal to 0 meters per second. Let's think about what I mean by that. So this thing is starting to go up, right? But you know that the force of gravity is trying to pull it down. So it's going up, but it's going slower and slower and slower and slower. And eventually it loses the fight with gravity. And so it's going to start going down, 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 down. Okay. And that is where we turn from going up to going down for a minute, a split second, right? We're going to be moving from a positive vertical velocity to a negative vertical velocity. And to go from positive to negative, you have to go through 0. And so that vertical velocity being 0 is what defines the peak for us. So if you're ever asked about the peak, remember that what I'm really asking is wherever that vertical velocity is 0. That's going to be super important. And again, that is another thing I would say, write in your notebook. Peak means vertical velocity is 0. Okay. So what do I know here? I have this, it's being launched at a velocity of 20 meters per second and an angle of 30 degrees. So what that means is the diagonal is 20, the angle is 30. So we need to find what that initial vertical velocity and initial horizontal velocity are. Horizontal is going to be 20 times the cosine of 30. Vertical is going to be 20 times the sine of 30. So that means our vertical velocity is 10 meters per second. And our horizontal velocity is, sorry, I'm in radians of all people. 17.3. For the record, this is the place I see things go wrong most on these problems is somehow this 20 meters per second ends up down in these problems. Once we use the 20 meters per second to find the horizontal and vertical initial, it should no longer exist. I should never see that again. Okay. Accelerations, still boring, still the same. I told you to write them down for a reason, I promise. I do have, yeah, there we go. Now, some little bonus information that is very specific to two specific points. My velocity at the peak is going to be 0. And my delta x at the ground, which is the other point I'm going to ask about, is going to equal 0. So in other words, ground level is when I've gone up and come back down. And I haven't actually moved anywhere vertically, right? I'm at the same height again. All right. So with that in mind, question B asks, how long until this reaches the ground again? And I'm going to go ahead and give you a minute, pause the video. All right, let's see what I can do here. I'm going to use equation number 2. This is a vertical question. Again, nothing here about horizontal in the question, but I do have an identifier for which of these extra pieces of information I can use. I can use anything that's true about the ground. Okay, so 0 equals, all right, initial velocity times time. Please remember to use your vertical initial velocity and 1/2 AT squared. So again, this is a quadratic. It doesn't have a C term, right? We talked about quadratics having like ax squared plus bx plus c, and this has an a and a b. It doesn't have a c. In some ways, that actually means it's a little easier to solve. If you wanted to factor this, you actually could. I'm going to go ahead and enter it in Desmos, which is by far my preferred technique. So if you look here, I put in 10x minus 4.9x squared, right? 10t minus 4.9t squared. And then I can look up here and I have, where is it equal to 0? Well, that's like, when is it on the x-axis? So these 2 points right here are the 2 points. So it's equal to 0 at time 0. Makes sense that we fired it off of the ground, yes. And at time 2.04 seconds. So t equals 0 and t equals 2.04. Both of those are correct physically. It was on the ground at both of those times. But when does it come back to the ground again? 2.04. And a reminder, when we're working with quadratics, part of the work is knowing which questions are correct mathematically, but don't make sense physically. All right. Next question is, when does the ball reach its peak? And I have 2 ways of doing this, and I think both are worth seeing. Go ahead and pause the video if you want to give a shot to a way that you might have. I think you probably have at least one idea of how you could do this. And now I'm going to go ahead and get started. So when does the ball reach its peak? It's when it reaches a velocity of 0. So I could do VI equals, or VF equals VI plus AT. So 0 equals 10 minus 9.8 t, and get an answer of t equals 1.02 seconds. This is fun because it always works. And in AP Physics, sometimes we have these like lopsided ones where it falls off of a cliff at an angle, and like this will always work even in those situations. But I have something working in my favor here, and that is symmetry, which is to say that it takes exactly as much time to go up as it does to go down in this problem. And so if I just take 2.04 and divide it by 2, that will also give me the right answer. This will always work on any question I give you in this class. AP Physics, it will take a step up. All right. How high is the ball's peak? Go ahead and, knowing that we now know the time, see if you can find how far we've traveled during that time vertically. Pause the video. Okay. So here we're looking for the height, which is going to be a delta x, the vertical delta x. And I'm going to use VIT plus 1/2 AT squared here. This is equation 2. So we know the initial vertical velocity. We now know the time at the peak. And so if we fill in, we will have all of our information. And this gives us an answer of eventually 5.1 meters. Now, I told you that Desmos happens to be my favorite way to do this. Let's see one of the reasons why. So we've got my friend right here. This is the graph that I already made and already showed you, right? And we already saw how it helps me find the 2 times that it's on the ground. It also has the time at the peak and the height at the peak. So 1.02 seconds for the time and 5.1 meters as the height. Kind of useful, isn't it? This is why, for me, that will always be a good solution, is to graph the quadratic, because it gives me so much more information than just the quadratic. All right, final question here is, what is the ball's total velocity at the ground? I'm going to give you a hint. You need to find the horizontal velocity at the ground and the vertical velocity at the ground, and then we're going to find the total. So why don't you go ahead and do that? Pause the video. Okay. Horizontal velocity, we've seen this before, but it never changes because there's no acceleration. So I don't really even need to do that calculation. I can just say it's the same. Vertical velocity, I do need to do. So the final velocity is going to equal initial velocity plus a t. Please remember to use your time for the ground here, not your time for the peak. You get an answer, by the way, that is really interesting to me. It's just the opposite of the initial vertical velocity. And that comes back to the symmetry. If it looks like this on its way up and it's symmetric, it looks just the opposite on the way down. Same horizontal, opposite vertical. That is something that you could just assume in these problems, for the record. You don't have to calculate that. You could just say, it's going to be the same, but negative. If you feel like you need to calculate it to feel good about it, that is also totally fine. All right, so then what's the total? Well, we could do our whole 17.3, 10, square them, etc. it ends up being the same, just pointing downward. For the record, this also is still 30 degrees. Okay, so these problems can look pretty tough, but because of the symmetry, so many things kind of simplify away to the point that they're always going to be the same or exactly opposite or half, or like there's all these little simplifications. Again, yes, if you are one of the brave souls who comes to take AP Physics with me in the next 3 years, we'll look at some situations where we can't make a lot of those assumptions. And you actually have all the tools here to deal with it anyway, right? We could have calculated this. We could have calculated this. We just don't have to at this point. One thing I might ask here that I realize I didn't put on this worksheet is how far does it travel horizontally between when it leaves the ground and when it hits the ground. What's cool is because there's no acceleration, it's really just a distance equals rate times time. So you would take your horizontal velocity, 17.3, and you'd multiply it by the time it was in the air, 2.04, and you can calculate pretty straightforward that it will be traveling 35.3 meters. Okay, so that is the one question I'm realizing isn't on this worksheet. We can look at that a little bit next week. All right, so give number 4 a shot while I grab a drink and I'll be back. All right, last question. So we've got a 10 meters per second, 40-degree angle. We need to do our horizontal and our vertical. Wow, that is a terrible triangle. I'm so sorry. So the horizontal is going to be 10 times the cosine of 40, which is 7.66. And the vertical is going to be 10 times the sine of 40, which is going to be 6.42. Accelerations are boring and the same. And again, we know our delta x at the ground is going to be 0. And our final velocity at the peak is going to be 0. Right? So those are actually 2 separate spots that could be asked about, but they're both vertical pieces of information. All right, how long till it reaches the ground again? We're going to do delta x equals VIT plus 1/2 AT squared. 0 equals, again, please only use numbers over here. This number ceases to exist. Like literally scratch it out on the piece of paper. You will look at it and you will try to use it. So once you've used it, get rid of it. Okay, so this is the quadratic that we're looking to solve. So if you're entering this in a quadratic formula or a quadratic equation solver, A is negative 4.9 and B is 6.42. And there is no C, so C is 0. But if you are entering it in Desmos, then we can just write 6.42x minus 4.9x squared. I will figure out, I'm still trying to think about exactly how, but I am going to figure out a way for you to be able to use like a Desmos on your final exam, since I know not all of you have graphing calculators. So that might be like 1 or 2 computers that are set up in graphing for Desmos, or figuring out a test mode or something, but I'm looking into that. All right, here's what I get. So I'm at the ground at 0 seconds. I would be worried if I wasn't. And I'm also at the ground at 1.3 seconds. So t equals 0 and t equals 1.32 are my 2 numerical answers, my mathematical answers, but that 1.32 is the one I'm actually concerned with. All right. When does it reach its final peak? Halfway in the middle, which is going to be 2.1. Oh, sorry. That's the answer. 0.65 seconds. How high is the ball's peak? Again, we can plug this in with some vertical information. And get our answer, or 2.1, the y coordinate of that peak. Okay, so 2.1 meters. And what's the ball's total velocity at the ground? It's still 10 meters per second. Again, here it will be 7.66 this way and 6.42 that way. Instead of at the beginning, it was this and this, right? So at the beginning, it was going up. Now it's going down. But it's the same. All right. Thank you all so much for your patience this week as I've been dealing with this. I'm super hopeful that I'll be back on Monday, ready for us to all hit the ground running and fill in any gaps that you feel like are there. Um, and I look forward to seeing you all then. Okay. Thanks, guys. Bye.